Welcome to this explainer. Okay, if you're learning to program, you've probably experienced that universal rite of passage, right? You're sitting at your keyboard, you type out a perfectly formatted, incredibly simple Hello World script, you hit run, and absolutely nothing happens. Or, even worse, a massive error pops up. It's a super common frustration, and honestly, it usually boils down to a really fundamental disconnect. You are writing instructions that your computer doesn't actually understand yet. So today, we're going to fix that disconnect by pulling back the curtain on one of the most powerful programming ecosystems in the world. So why can't your machine just read what you typed? I mean, think about it. When we write code, we're basically using an English-like language. We write commands like system.out_print. It makes total sense to us. But your underlying hardware, your actual physical laptop, desktop, or phone, it operates entirely on electrical signals, literally ones and zeros. And right between your human-readable code and that hardware sits your operating system, whether that's Windows, Mac, or Linux. Each operating system has its own unique language and rules. So your readable code, it's complete gibberish to them. To bridge this massive communication gap, Java introduced a brilliantly elegant architecture. Okay, let's dive into this. Here's our roadmap to untangling Java's architecture. Number 1, the platform independence paradox. 2, from code to bytecode. 3, finding the entry point. 4, inside the Java kitchen. And finally, 5, write once, run anywhere. Starting with section 1, the platform independence paradox, and exactly how Java speaks to every OS. To really understand Java, you kind of have to look at the hierarchy from the bottom up. Down at the very base, you have your physical hardware, your Mac, your Windows PC, or your phone. Sitting directly on top of that hardware is your operating system. Now here is where Java introduces its secret weapon. Instead of trying to write code that speaks directly to Windows and then writing entirely separate code that speaks to a Mac, Java slaps a third layer right on top of the OS. This layer is called the Java Virtual Machine, or JVM. The JVM acts as this universal, dedicated translator. Its entire job in life is just to sit on your machine and execute Java code. Now, you might be wondering about the paradox here. Java is famous for being platform independent, meaning your one single Java application can run on any machine anywhere. But here's the crazy part. It can only do this because the JVM itself is completely platform dependent. There is no way you can run a Mac JVM on a Windows computer, and you can't run a PC JVM on iOS. The JVM is specifically custom built for each distinct operating system. You install the correct JVM for your specific OS, and then that JVM allows your independent Java application to run seamlessly. Moving on to section 2, from code to bytecode. This is all about translating English to machine speak. Remember just a second ago when I said the JVM is your translator? Well, actually, scratch that. There's a little catch. The JVM absolutely refuses to read your original Java code. It won't even look at it. Here's what actually goes down. Step 1. You, the programmer, write your highly readable English-like code and save it as a .java file. Step 2. You pass that file through the Java compiler, specifically a tool called Javec. Step 3. The compiler translates your entire script and creates a brand new file with a .class extension. This new file is called bytecode. Finally, in step 4, you hand that bytecode over to the JVM to do the actual execution. Let's get crystal clear on what bytecode actually is. It's an intermediate format. If you were to open that .class file on your screen right now, it would look like total unreadable gibberish to a normal human being. But to the JVM, it's absolute poetry. The Java compiler takes on the heavy lifting of translating your human-readable logic into this highly optimized intermediate bytecode, which the JVM can process incredibly fast. Section 3. Finding the entry point. Or, how does the JVM even know where to start? Imagine you're building a massive application, right? It's got hundreds or maybe even thousands of .class files. When you tell the JVM to run, it doesn't just randomly guess where to begin. Now, what's really interesting about this is that it frantically searches your specified starting file for one specific, incredibly strict method signature. It's looking for public static void main. If this exact phrasing isn't there, the JVM literally throws its hands up and refuses to run. You see, Java is an incredibly structured, object-oriented language, and it enforces strict rules before it will ever execute your code. First, you absolutely must specify the starting file. Second, because Java demands that everything be an object, that file has to contain a properly formatted class. And third, nested directly inside that class, you must have that exact main method signature we just talked about. It's literally the front door to your application, and without it, the JVM cannot enter. All right, Section 4, inside the Java kitchen. It is time to decode the alphabet soup of JDK, JRE, and JVM. To really wrap our heads around the difference between the JDK, the JRE, and the JVM, we need a solid analogy. Imagine running a restaurant. The chef's master kitchen represents the Java Development Kit, or JDK. This is the complete toolkit a developer needs to actually create the meal. It's the knives, the chopping blocks, and that Java compiler we talked about earlier. But the dining experience, that's the Java Runtime Environment, or JRE. This is what the end user needs to simply consume or run the application. So let's formally define the JRE. The Java Runtime Environment is the actual physical space where your application runs. You can think of it as the physical kitchen itself. It's not just an empty room, though. It comes fully stocked with the extra ingredients and shelves of standard libraries that your application might need to pull from while it's executing. And this brilliantly illustrates how the whole shebang fits together. The entire kitchen space is your JRE. The extra ingredient shelves are the libraries your code pulls from. And sitting right in the middle of that kitchen is the stove. That's the JVM. The stove is the engine doing the actual cooking, the actual execution of your bytecode. But hey, a stove can't make a complex meal like biryani just floating in an empty void, right? It needs the surrounding kitchen, the environment, to function. The JVM needs the JRE. Now let's see how this builds into a perfect nesting doll structure. At the absolute core, you have the JVM, the execution engine. Wrapped around that is the JRE, providing all the necessary libraries so the JVM can actually run. This is what your standard users install. And finally, wrapped around that is the massive outer box, the JDK. That includes the JRE plus all the compilers and tools developers need to write the code in the first place. Finally, Section 5, write once, run anywhere, the absolute magic of WAURA. Because of this nesting doll architecture, Java achieved something truly monumental. Write once, run anywhere, or WOOR. As a developer, you use the hefty JDK on your machine to write and compile your code into bytecode just one single time. Then, you can take that compiled .class file and hand it to a friend. And guess what? Your friend doesn't need the massive JDK. They don't need the development tools. As long as their computer has the lightweight JRE installed, which, remember, contains the JVM, they can seamlessly run your code. It doesn't matter if you wrote it on a Mac and they're running it on a Windows PC. The local JRE and JVM handle the rest. It's brilliant. The Java ecosystem might seem like chaotic alphabet soup at first glance, but beneath the surface, it's honestly a masterclass in software architecture. You now understand how your readable code gets translated, exactly how the execution engine searches for an entry point, and why the JVM relies on the JRE environment to perform its cross-platform magic. You know exactly how this kitchen is organized. So the only question left for you is, what are you going to cook up next? Thank you so much for joining us for this explainer, and happy coding!